Good morning. Today, me and my teammate Mahir Thakur, we will be talking about superscalar and super pipeline architectures. Through this presentation, we will be examining how these architectures achieve instruction level parallelism to boost our system performances. What is instruction level parallelism? So it is at heart of the modern processor design aiming to execute multiple instructions simultaneously. So techniques like branch prediction and data flow contribute to the ILP. But today we'll mainly focus on superscalar and super pipeline architectures. These are two primary ways to achieve ILP, uh, like by enhancing performance, by exploiting parallelism within instruction streams, and parallelism in processor design is like having multiple workers in a kitchen instead of just one, and all are preparing different parts of a meal at the same time to finish to achieve the end product more efficiently and in a faster way. There are uh, two types of parallelism. First is no parallelism, and one is parallelism. No parallelism is basically like having one cook preparing an entire meal alone, where he has to cut vegetables, cook rice, and then prepare the curry. And since there is only one cook, he has to do everything step by step, which takes a very long time. On the other hand, where there is parallelism, imagine there are three cooks, where one chops the vegetables, one cooks the rice, and third prepares the curry, and all of them are working at the same time towards cooking the same meal. So this increases efficiency. Now the superscalar architecture will be explained by Mahir.
Uh, Superscalar architecture is defined by its ability to issue and execute multiple instructions per clock cycle. This is achieved through multiple execution units like ALUs and FPUs. Instruction fetching and decoding occur in parallel, enabling dynamic scheduling and out of order execution. This allows the processor to find and execute independent instructions concurrently, maximizing throughput. So now we will understand superscalar in simple language. The superscalar processor is like a factory that has multiple assembly lines working at the same time. Instead of assembling one product at a time, different workers, that is functional unit, assemble multiple products simultaneously. For example, if there is a single worker that can assemble one vehicle per hour, then it will be called scalar processing. If we add more workers and assembly lines, multiple bicycle can be built at same time. This is called superscalar processing. Now, if the factory is well organized, so worker don't wait for each other due to missing parts. So this will be called instruction dependencies. The key idea is a superscalar processor fetches and executes multiple instructions at the same time using parallel execution units. So now we will discuss about challenges and advantages of superscalar architecture. Superscalar architecture shine in exploiting dynamic parallelism, adapting to varying instruction patterns effectively. Compared to other dynamic techniques, the hardware is relatively simple. However, managing complex instruction dependencies and the associated hardware complexity for dynamic scheduling pose significant challenges. Data dependencies and branch misprediction can also limit performance. The advantages for superscalar architecture is it exploits dynamic parallelism effectively, relatively simple hardware compared to other dynamic techniques. Superscalar processor can execute multiple instructions per clock cycle, significantly improving instruction throughput. The challenges of superscalar architecture is it has complex instruction dependencies, hardware complexity for dynamic scheduling, limited by data dependencies and branch mispredictions. Decoding and issuing multiple instructions per cycle requires sophisticated hardware to check dependencies and schedule execution. Now, my teammate Parth Nair will discuss about super pipeline architecture.
Super pipeline architecture basically achieves faster clock cycles through deeper pipeline stages. This involves increasing the number of pipeline stages for allowing for a faster clock speed compared to traditional pipelines. The key is to divide instruction processing into smaller steps, so each stage does smaller amount of work. This enables a higher clock frequency and potentially a greater throughput. To understand this in a simple language, a super pipeline processor is like a factory that breaks down the assembly process into smaller steps. So each worker does smaller part of the job but at a more faster rate. Instead of one worker completing a bicycle in an hour, we divide the work into finer steps and make each worker complete the part in less time. To put this into an example, a bike assembly has four steps: frame, chain, and wheels, and paint. If each step takes 1 hour, the factory produces one bicycle per hour. But if we make each step twice as fast, that means 30 minutes per step, the factory now produces two bicycles per hour. This is called super pipelining, where pipeline stages allow faster processing. So the key idea here is a super pipeline processor increases the number of pipeline stages, allowing instructions to be completed faster, similarly to a finely tuned assembly line. The challenges and the advantages here are: the super pipeline architecture benefits from higher clock speeds, leading to significant performance gains, and are relatively simple to implement. However, they face challenges such as increased pipeline hazards, including data control and structural hazards, and higher penalties for branch predictions uh, for mispredictions. Diminishing returns can also occur as pipeline health increases. The comparison will be given by Mahir.
So now we will discuss superscalar versus super pipeline comparison. Superscalar and super pipeline architecture differ significantly in instruction issue, clock speed, hardware complexity, and dependence handling. Superscalar processor issue multiple instructions with moderate clock speed and complex hardware, while super pipeline architecture, on the other hand, issue single instruction but boost high clock speeds and relatively simple hardware. Dynamic dependence handling is characteristic of superscalar, while superpipeline relies more on static handling. So now we will understand in simple terms. So super pipeline architecture breaks pipeline in smaller stages, executes one instruction per cycle but at higher frequency. It faces higher pipeline hazard while it benefits from increased clock speed. Example of super pipeline architecture is Intel Pentium 4. While superscalar architecture executes multiple instructions per cycle, it uses multiple execution units like ALUs and FPUs, which improves instruction level parallelism, that is ILP. It needs complex instruction scheduling. The example for superscalar architecture is Intel Core and AMD Ryzen. Now we will discuss clock cycle time and pipeline stages impact on performance. So for superscalar architecture, shorter clock cycle time, that is moderate frequency. It has limited pipeline stages, approx 5 to 10. The performance improves with parallel execution. Efficiency depends on instruction independence. The more execution units gives higher throughput, and in super pipeline architecture it has higher clock speed, that is shorter cycle time. It has more pipeline stages, approx 10 to 30. It reduces instruction latency but increases hazards. It has branch mispredictions and dependencies can stall performances. The more stages in super pipeline architecture gives higher frequency but more hazards. So now my teammate Parth will discuss about case studies and examples.
Okay, so processors like Intel Pentium and AMD Athlon exemplify superscalar architecture, dynamically scheduling instructions for optimal performance. The Intel Pentium 4, while historically being a super pipeline example, incorporated superscalar features. Modern processors like the Intel Core i series blend both the techniques of super pipeline and superscalar architectures, showcasing an evolution in the processor design. They basically leverage the strengths of both approaches. For the conclusion here, superscalar and super pipeline architectures aim to improve the performance of the systems to take different approaches. Where superscalar is more effective for instruction throughput through parallel execution, where three different or four different instructions are being worked on simultaneously, whereas super pipeline effectively optimizes clock speed, where every instruction takes ha- to say half the amount of time to execute, which which increases the efficiency again. A- but it also faces diminishing returns due to pipeline hazards. So modern processors use a hybrid approach to balance both techniques, where of dynamic scheduling from superscalar and faster clock speeds from super pipeline. Thank you.